Welcome. In this next lesson, we're going to look at counting. And we're going to start with the fundamental counting rule. The fundamental counting rule for a sequence of two events is when the first event can occur in m ways, the second event can occur in n ways, then the ways that the events can occur together, the first event and then the second, the number of ways that they can occur is m times n. Let's take a look at an example of this. Okay, let's start with, imagine you're trying to remember a friend's phone number. You know the first three digits are 206. The question is the following. What are the last four digits? We know that each of the four digits in the phone number can be any number from 0 to 9. So there are 10 possible digits or numbers for each digit. What is the probability that you select the correct sequence of these four numbers? So your telephone number starts with a 206, and then you have four more numbers, or four more digits. There's our first. I'm going to copy that, and here's our second, paste, and our third number, or digit in the phone number, and a fourth digit. So we're trying to determine how many different ways can we select these four digits. Well, in the first digit, there are 10 ways to select the first digit. In the second digit of our phone number, there are 10 possible numbers that could go in there, also 0 to 9. In the third, there are also 10, and in the fourth, there are 10 ways of selecting the fourth. So the total number of ways that we can select it, okay, is 10 times 10 times 10 times 10. This is our fundamental counting rule. So this is going to be 10 raised to the fourth, which is 10,000. So that's the total number of ways that we can select these four digits. If we want to know what is the probability that on our first try we select the correct four numbers, or the correct four digits. Well, there's only one way we can select the correct ones. That's our event space size. And our sample size, there are 10,000 ways that we can select. There are 10,000 ways that we can select our four digits. That means the probability, we move the decimal place over if you're figuring this out. We want to have a 1 in the denominator, so here's our starting point. If we move the decimal point over 1, 2, 3, 4, we'll get a 1 on the bottom, which means we've got to move the decimal point over 4 times on the 1, which gives us 0.1, 2, 3, and here's our fourth one. That's the probability, and that probability can be written as, if we move the decimal point over twice, this time to get percentage, 1, 2, the percentage or probability is 0.01%. So it is highly unlikely that we will be able to guess the four digits, the last four digits of someone's telephone number. All right, let's try something a little bit different. If we go back, the problem we just saw is this is called without replacement. We're trying to find something without replacement. That is to say, let me write that down, that's important. This problem is what we would consider a counting problem without replacement. And what without replacement means that when I went to select that first digit, that would be this one right here. When I went to select it, I knew I had any number from 0 to 9, so 10 possible digits. Let's say I picked a 9 and put a 9 in there. Well, when I go to select my second digit, 9 is still available. So actually, I made a mistake here. This should be, let me fix that. This should actually be with replacement, excuse me. Let's fix that. Okay, so this is a with replacement problem. Because what happened is, in the first place, I selected 0 to 9. I could have a digit from 0 to 9 in this position. And so there were 10 possible. And when I went to the second digit, and I went to select a number, I could still select anything from 0 to 9. If I already used a digit, say 9 or 5, any digit, well, that digit exists again for me to use in my second place. In other words, I could have the same number used more than once. And that is considered with replacement. In other words, if I go to take a 9, for example, well, 9 is replaced so that I can take it again. So let's go to the problem that is, this one is different. This problem is without replacement, okay? So just want to show you the difference. So in this case, you're selecting 3 drinks from a vending machine. We're going to select 3 drinks. The machine is almost empty. It has a total of only 3 bottles left, so it only has 3 bottles left in the machine. These last 3 bottles are each different drinks. These different drinks are, there's Coke, ginger ale, or water. These are the last 3 drinks. If you randomly select each drink, what is the probability that your first choice is Coke, your second choice, your first choice is Coke, your second choice is ginger ale, and your third choice is water? Okay, so our choices are Coke, we'll use a C, G for ginger ale, and W for water. So we want to know, what is the probability that our first choice is Coke and our second choice will be ginger ale and our third choice will be water. So we want to find out what is the probability of this. So let me move this up here. When we're looking at probability, it's a ratio of our event space size over our sample space size. Okay, so we want to know, I'm going to write this is the size of our event. That is the outcome we're looking for. Coke, ginger ale, and then water. And this is the size of our sample, so all possible ways that we can select these. Well, our event size is 1. There's only one way that we can select first Coke, then ginger ale, then water. So we put a 1 on top. But we want to know how many ways can we select first, can we select Coke, ginger ale, and water? Well, the actual number of items that we have here is 3. There are 3 items, okay? And we're going to select 1, then another item, and then another item, okay? So if you think about it, there are 3 ways that we can select our first drink: Coke, ginger ale, or water. So one of 3 ways. But once we've done that, if let's say we selected ginger ale first, there are only 2 left. So in our second spot, there are only 2 available items that we could select for our second drink. And once we've selected the second drink, there's only 1 left in the machine. So there's 1 way we can select the last drink. So 3 times 2 is 6, times 1 is 6. So here we have our probability is 1/6. Now this is a problem. This is without replacement. So that without replacement means that once I've taken that first drink, that drink is gone and there are only 2 left. I don't replace that drink. Remember, the vending machine is just about empty. So this is without replacement. And replacement. Okay, so let's finish this off. Let me make this give ourselves a little bit more room here and move this 1/6 over. And the probability of 1/6 is 1 divided by 6. And I'll put that in my calculator. 1 divided by 6 is, excuse me, is equal to 0.166. And this 6 is repeating. Okay, so we can sort of round this off to 0.16 and make the last 6 a 7. We round to 3 significant digits. And if we want to put this in percentage, we will move our decimal point over twice, and it's 16.7%. So this is the probability, 16.7% is the probability that we will select in our first round, if we randomly select each of the 3 drinks, that we will select first Coke, then ginger ale, and then water. Now notice the difference between these 2 counting rules. In this case, without replacement, it's 3 times 2 times 1. Each time we multiply by 1 less than what we had before. With replacement, a little bit different. Here with replacement, we just keep multiplying by n times n times n times n, because we replace each time, so we end up with n more to select from. So with replacement, that's what this is, versus without replacement, and it's n times n minus 1 times n minus 2, etc. So this without replacement brings us into the factorial symbol. And the factorial symbol is an exclamation point. And an example, when we use the factorial symbol, the exclamation point, it denotes the product of a sequence of decreasing positive whole numbers. For example, 5 factorial is equal to, I better put the times in there, 5, let me zoom in on this, times 4 times 3 times 2 times 1. And by definition, 0 factorial always equals 1. So going back to our previous problem, in fact, our 3 times 2 times 1 is actually equal to 3 factorial. 3 times 2 times 1. And so we can do a few examples of that over here. If I wanted to determine what is 4 factorial, it's equal to 4 times 3 times 2 times 1. And of course, 4 times 3 is 12, times 2 is 24. So this is an example of factorial, which we will use in counting. And of course, we clearly used it here. 3 factorial is the number of possible combinations. Number of possible sequences, not a combination, but number of possible ways or orders in which we can select 3 things. The factorial rule says the following: a collection of n different items can be arranged in n factorial different ways. Again, this is without replacement. So without replacement, if we have n items, so without replacement, if we have n different, they have to be different, n different items, and we want to know how many different ways can we select those n different items, it's equal to n factorial. In other words, is equal to n times n minus 1 times n minus 2 times n minus 3, and we keep going until we get to n minus n, which actually is 0, and that is our n factorial. An example of this is if we have n is equal to 6, we want to know how many different ways can we select 6 items without replacement. It's going to be equal to n factorial, which is 6 factorial, which is 6 times 6 minus 1, which is 5, times 5 minus 1, or n minus, or 6 minus 2, which is 4, and we keep going, times 3, times 2, times 1. If we want, we can say times, well, we wouldn't want it to be 0 factorial, but we don't usually do that. 0 factorial is, in fact, 1. Okay, here's another example. You're shopping for school supplies. You decide to visit 3 different stores: Walmart, Staples, and Best Buy. In how many different orders can you visit these 3 stores? Well, the stores are Walmart, Staples, and Best Buy. So there are 3 choices, n is 3. So how many different ways? Well, if you're going to go to all 3 stores, you can visit the first choice can be one of either of these stores, Walmart, Staples, or Best Buy. But once you've gone to visit one of them, there are only 2 left. So there's 2 different possible stores you could go to for the second time, and then once you've selected that second store, there's only 1 store left. So this, of course, is 3 factorial, which is 3 times 2, which is 6, times 1 is still 6. Okay, according to the factorial rule, n different items can be arranged in n factorial different ways. What if we have n different items and we only want to select some of them instead of all of them? For example, what if we were in the mall with 30 stores? Okay, so n is 30. And we only have time to visit 4 of these stores. Well, let's use the letter R. We want to go to 4 of these stores. How many different arrangements of visiting the stores is possible? Well, we're only going to visit 4, so R is for 1, 2, 3, 4. We're only going to visit 4 stores. Well, there are 30 different stores that we can select from to visit the first store. Once we've visited that store, we don't want to visit again. There are 29 stores left. Once we've visited that store, there are 28 stores left to visit. So for our third choice, we have 28 stores we could visit. And then finally, for our first choice, we visited 3 stores. So now we're going to visit a possible 1 out of 27 stores. So in this case, this is not n factorial. In fact, what this is equal to is n factorial divided by n minus r factorial. What does that mean? Let me move this around a little bit. Let me take what I just wrote. We'll move it down here. And what is this? N factorial is 30 factorial. If I divide 30 factorial by n minus r factorial, well, n minus r is, let me turn off the straightener, is 30 minus 4 factorial. Okay, so in the numerator I have 30 factorial, and in the denominator I have 30 minus 4, and that's 26 factorial. Now let's look at what's going on here. If I write out 30 factorial, I get 30 times 29 times 28 times 27 times, let's stop at 26. Now we could keep going after 26, but I'll just put a factorial after that to say it actually keeps going all the way down to 1 factorial. And if I divide this by the denominator, which is 26 factorial, we can see that 26 factorial cancels out with 26 factorial. The numerator and denominator cancel each other out. And what happens here? Well, the result is 30 times 29 times 28 times 27, which is what we already determined to be the number of ways that we could visit 4 stores out of 30. So this is another factorial rule when we're not going to visit n stores. We're going to visit fewer stores than we actually have available to visit. This brings us into our next section of permutations. So I'm going to stop this video and I'll continue on to permutations in our next lesson.